Welcome to in-depth lecture on climate change studies. Today, let's talk about Kirchhoffs Law. What is Kirchhoffs Law? And if you have studied electricity, you may have heard that Kirchhoffs Law of current, Kirchhoffs Law of voltage, and that is a contribution in the electricity, who extended Ohm's law to a more sophisticated electronic circuit. But today I will focus on his contribution in thermodynamics, in particular, the so-called thermal radiation. Okay. Thermal radiation is not just purely thermal physics. Radiation is actually, by definition, is electromagnetic waves. So you can see that the Kirchhoffs law in this context covers both thermodynamics and electromagnetism. Okay, in particular, the Maxwell's theory of the electromagnetic wave. And today, perhaps I will just try to introduce the idea of the Kirchhoffs and discuss the limitation of this Kirchhoffs law, so that we have some background of the theory at the core of the climate change studies. So let's consider the star, and due to certain internal heat thermal source, say the nuclear reaction, and the inner part can become very hot, and gradually, and the whole star getting warmed. And according to the study, according to the thermodynamics, and if the surrounding temperature is lower than the object, then the radiation would occur. So in this case, and this, if we just illustrate that radiation, so radiation will go around to all directions as long as the temperature is lower than this object. So that is what we call the thermal radiation in space, in vacuum. So the reason being that because in this case, they got absorption. So they got absorption here. Can we just write? So because they got absorption, A for absorption. And the radiation is called, you can also consider radiation as emission. So we can use E for emission. So emission in all directions. And gradually, of course, and this thermal transfer process will gradually reach to a certain equilibrium. In that case, the temperature will be fixed. So at least the surface temperature will be fixed, although the temperature gradients still exist inside this star. So at that point, and you can apply that another basic law called Stephen-Boltzmann law, and which that intensity of radiation is proportional to the temperature of the body. But today we are not talking about Stephen-Boltzmann law. Instead, we're focused on Kirchhoffs law. Okay, so what does the Kirchhoffs law say? They say we consider two scenarios. One is we consider opaque object nearby. So this is opaque object. And when we say opaque, I mean that that is opaque right down here. Opaque. Then when I mean opaque, I mean that there's no transmission. So basically, if we just indicate that the incoming radiation that is coming to this object, that is incoming radiation. And if this opaque, the transmission will be 0. So there's no transmission, but reflection will occur, right? So if you just use a different color to indicate the absorption, this reflection will occur. In the meantime, absorption will occur. So there's at least 2 mechanisms is associated with this interaction between the opaque object and the incoming radiation. So absorption occur internally, reflection occur on the surface. So there's incoming radiation. Okay, according to energy conservation law, then there's a simple balance condition, that is incoming radiation intensity were equal to the sum of absorptance. But this power equation, rather, this is just a power equation. So the total energy absorbed per unit time will simply satisfy these equations. Okay. And of course, and in the meantime, according to Stefan Boltzmann law, and by the time the temperature reached to equilibrium temperature, I mean this object, and then they will start to emit. Okay, actually, as now the temperature is now above the absolute zero, the radiation of this object star. So I just use different color. Can we use a purple color to represent the radiation of this object? That's radiation. Of course, radiation go all directions, But if we just consider these opaque objects, the length is infinitely large, so we can only consider that radiation perpendicular to the surface of object. So we denote this emission, it's called a thermal emission, as E. Okay. Now this is different from the emission of E, so this is the emission from the opaque object. So this is can be called E null, that is object from this star in the distance. And in physics, many studies have been done in the 19th century to try to establish the relation between the absorption and emission. Kirchhoffs Law is one of them. So in short, as if you're just interested in the power of the power relation, so Kirchhoffs Law in this case can be simply written as the emission or the absorption were simply equal to the emission for the opaque object. So that is a Kirchhoffs law. There are many forms of Kirchhoffs law, and this is one of them. Okay, now if you divide that every equation by the I, with regard to the coefficient. So if you divide that by I, for example, the first equation can be, if you divide by that, become 1 or equal to, and this time A over I became the coefficient of absorption. Can we use A? Sometimes we can use alpha, okay, A for absorption. And the second term becomes R. Sometimes they use rho, but they represent the same thing. It's called reflectivity. So that is in the percentage form. So if you substitute the Kirchhoffs law, so this is a first form of Kirchhoffs law. And then we can rewrite this power balance equation as simple as that. So that will become, so if you just rearrange that, you will become that is emission, the coefficient of emission. We can use epsilon, or simply equal to 1 minus reflectivity of this opaque substance, I can tell you this would be the case. This would be the useful model when you describe the interaction of the solar radiation at the surface of Earth. Okay, so we'll talk about that in the future. But today, let's just consider another scenario. That is, if the media is not completely opaque, but transparent, semi-transparent at least. So we can draw another. Let's consider another scenario. Okay, in this case, This can be in infinity. It's very long, so we will just focus on part of that. So in this case, the incoming radiation from the star can be denoted by an arrow. Okay, that is the incoming radiation. After that, because it's not opaque, they got transmission. So part of them will be transmitted. And in this way, still, and there are some reflection. But in general, if we're dealing with transparent or semi-transparent media, the reflection can be, the reflection, can we just put the reflection here? But the reflection should be very small, relatively speaking, very small. Okay, so that is the situation where the transmission must be taken into account. And so this is incoming radiation. This is incoming radiation, either intensity or the power. And that is transmission. I use capital T here. I probably just use the T slightly different from this is just for the transmission, and this is reflection. In this case, we can generally assume that the reflection is almost zero. Absorption still occur, okay, do you agree? It's just like the glass, like in the roof of the greenhouse. So you got, they got a transparent glass as a roof. So reflection can be considered as small to simplify this argument. So in this case, and we can argue that the incoming intensity, again, this is just a power balance condition, were equal to absorption plus transmission, right? Because in this case, we still can take a reflection here, but then we can use this approximated relation. That is A were equal to A plus T. R can be considered as, negligible, small, too small. Now, then use the same notation and work out the coefficient. Then we will got this 1 equal to A and plus tau here. Okay. So in this way, and we got the similar graph. So we got from this here by invoking invoke Kirchhoffs Law. So we just invoke Kirchhoffs Law, that is the coefficient of the absorption is equal to coefficient of emission. Then in this way, we got the epsilon were equal to, or perhaps sometimes we are interested to know the function of the transmission or transmittance. So we're talking about this. There are many names, but we just use a coefficient for time being, so that the coefficient of transmission can be simply written as 1 minus epsilon. Epsilon is a coefficient of emission. So, but if you just in this discussing, we just considered all radiation of all possible wavelengths. So we consider the entire electromagnetic wave. So sometime if we are interested in particular wavelengths or frequency, and this formula can also be written as, so you can just put the lambda here, just indicate that became wavelength specific. Okay, and that's another form of the Kirchhoffs Law. So in this case, so we can also write this as tau lambda equal to 1 minus epsilon lambda. So if you draw the graph, if you just consider this case, and we just a graph here, if I just draw a simple dependence, so this would be the vertical axis, where they present the transmittance. Okay, I talk of transmittance. Transmittance is just the proper name for it's a ratio of how much energy transmitted compared with the incoming radiation. So it's called transmittance. transmittance. And epsilon here, you can call it formally called as a emissivity. Good. Emissivity. Okay. So if you just use this diagram, you can find that the simple linear dependence. If this is 1, or this is 100%, so this is if this is 1, is the origin, this is 1, and you can get the very simple dependence between the transmittance and emissivity. It's a linear relation. See, all of these simple relation come from the Kirchhoffs law, that by assuming that the power of absorption is equal to the power of emission. But things can get very complicated, because in this discussion, we haven't talked about the condition when this assumption is valid, right? So let's talk about a little bit of the generalized form of Kirchhoffs law. So in general, if you look for the original paper by Kirchhoffs, and he argued that the ratio of the power of emission and the power of the absorption, can use A here, must be equal to a universal function. So F, that is just a variable of temperature of the material, and in this case, in the particular wavelength. So this is the general form of the Kirchhoffs law. So this you have to be aware that they are not just simply equal to each other. Actually, they are proportional to a function. And in his statement that if you look for the original paper, so this function is called the universal function. So this function is a universal function, which implies it is independent of the material and the property of material, geometry of material. So this law, Kirchhoffs law, didn't talking about the particular material or particular shape of material. But if you look into his study, you will find that this is based on the assumption that reflection can be completely ignored. So this is condition. This general form of Kirchhoffs law is assumed that reflection is not the issue. So that is conditional. So that provided that reflection is always 0. Okay. So, and interesting enough, and many years later, and by his student Max Planck, this so-called universality has been achieved by considering the so-called black body radiation. So that is, can we address that is Planck's contribution, and that is U represent the energy density at a particular wavelength that can be indeed written as a function, which is nowadays it's called Planck function. Planck function, can we use a B here? That is a T and lambda. So that is a Planck function. Again, it is it's very useful. You can find the Planck function in many theoretical studies about the climate change. So that is the link between the Kirchhoffs law and the Max Planck's law about black body radiation. Now here for the first time, we mentioned the color. So this is a formula is for the very interesting. We can talk about more today. So this is called the black body. So black body radiation. Black body radiation. So what is a black body? Why we mention the color black? That is because in Kirchhoffs law, in general form of Kirchhoffs law, he didn't take into account of reflection. So that's why. So what material could be a better candidate for the for this particular under this condition? And the dark one. Okay, when we wear the dark shirt, you can hardly see detail of on this black material. You can only see my tie and the shirt. That's right. That's because the color of this object is dark. So to some extent, the dark material, all the dark material can be considered approximately as a black body. But bear in mind, black body is ideal model in physics since Kirchhoffs. Black body refer the ideal material that the absorbed energy by this black body can be 100% be re-eliminated. Okay, so that is similar to the you can hardly find any energy to describe what is a black body, but in my opinion, something wrong with this color. Okay, the reason they mention the black, and by implication, they imply that that is that would be equivalent to say the reflectivity zero, but this is not necessarily the case, because black is is just, we're talking about the, if we consider radiation as an electromagnetic wave, okay, so black is just the idea in the visible light, okay, in the context of visible light, okay. See, how can you make that? How can make the judgment that the black body is also the perfect, with also the perfect object can absorb the energy other than visible light region. So this is my first remark, that the black body is very primitive ideas, and which was introduced before people fully understand that the interaction between the thermal motion and electromagnetic phenomena, namely the thermal radiation. So actually, thermal radiation is still to be further explored, because even we got the Kirchhoffs Law, we got the Planck's black body radiation laws, and some link was still there, was still missing. Okay, so that is why Albert Einstein later he introduced his coefficient of the emission and absorption, and that indicated that in the original form of Kirchhoffs law and Max Planck's black body law, that there's no clear description or explanation and of the reason that or the theory why the thermal motion can be spontaneously transformed into the electromagnetic wave, and so that is probably an introduction to the Kirchhoffs law. And if you are interested to some other issues, and we can continue to talk about these issues. So today I'm going to stop here. Thank you for viewing, and goodbye.